Okay, can we start now?
Yes, please, whenever you're ready.
Sure. Well, thank you, Zoraida. Thank you, Matan, for inviting me, and thank you, Danny, for a great first talk of the day. Um, Thank you for everyone who joined us today at uh, this time, whatever it may be for you. I will talk to you about this classical notion of Tukey's depth, or half space depth, and the closely related notion of Tukey's median. And in the end of the talk, I will talk about some new potential directions and extensions of this classical research direction. And along the way, I will try to mention several open questions that would be interesting, at least for me personally, uh, to answer. And there may be, if you have any ideas, or maybe you already know the solution, please let me know. So as a prologue, let me start talking from this main motivation, at least this partially serves as a motivation for me. The very traditional basic problem in statistics, the problem of mean estimation. Let's say we have a sample of an ID sample from the normal population with mean, mu, and covariance sigma. I want to estimate the mean, and the key quantity here that I want to emphasize is this notion of the effective rank. So if sigma is a covariance matrix of a normal distribution, then this covariance matrix may have a lot of small eigenvalues, and then the idea is that basically the samples from my distribution can look like this. So there can be some low-dimensional subspace that is spanned by the eigenvectors that correspond to large eigenvalues, and then the samples will live close to this high-dimensional subspace. In this case, this picture can be characterized by basically saying that the effective rank, my covariance matrix, is small. The effective rank being the trace divided by the maximal eigenvalue of sigma. So this is the way to characterize, if you want, the intrinsic dimensionality of the data. And in this case, we know that the sample mean for the Gaussians, it essentially respects such intrinsic dimension in a way that the concentration of the sample mean around its population counterpart is governed by this Gaussian complexity term that Danny talked about, which is in this case governed by this effective rank of the covariance matrix plus this deviation term, that is governed by the spectral norm or the maximal eigenvalue of the covariance matrix. So essentially, if you want the picture, the picture looks something like this. We know that the data lives, in this case, if this is an ellipse that is associated with the covariance matrix of the data, and this is the sphere of radius that appears on the right hand side of the bound. Then we know that the sample mean must live somewhere in these gray shaded areas. We want to imagine this visually. Okay, so what is the issue is that, of course, that we often have noisy and corrupted data, and that's why we have this wonderful subject of robust statistics. And one way that we can model noisy and corrupted data is to say that instead of observing an IID sample, we actually observed a sample for which the epsilon fraction of the data have been replaced by potentially arbitrary values, which we can encode in this condition. And we want to have algorithms that are stable in such a framework, that perform well even if the data are corrupted. In particular, for the problem of mean estimation, the state-of-the-art algorithm of the optimal bound that we'll be aiming to get would be the bound of this form. So we'll compare to the bound for the Gaussian sample mean, that is what we are aiming to get in the contamination-free framework. In this framework with outliers, we have an additional epsilon term, and the key point here is that we want this epsilon term to essentially come in a dimension-free way. So this epsilon is not multiplied by any dimensional factor, just by the scale factor given by the spectral norm of the covariance. Now, if I look at the, say, sample from bivariate normal distribution, and I compute the sample mean, then I can make the sample mean to be as far away from the true population mean as possible. So what we would like to have, an estimator that is maybe somewhere here, the blue point, close to the population center, while the sample mean will be somewhere here, far away from the population center. And the one of the estimators that is a good candidate for the role of this robust estimator, at least. I think my screen sharing has stopped. Let me try again. Okay. I think it is back now. So one estimator that we think is a good candidate for this role is called Tukey's median. I will explain in the next few slides what it is. And this what I call the folklore conjecture that this Tukey's median does satisfy under some additional minor assumptions that I will mention in passing. But basically, the folklore conjecture that Tukey's median respects the geometry of the data in a way that it depends optimally on this intrinsic dimension, or on the effective rank of the data, and also depends in an optimal way on the fraction of contamination. Okay, any questions up until this point? All right, so then so to understand Tukey's median, let us try to think about the simple one-dimensional case, namely how do we order data? If I have a univariate sample in R, then let's say the sample is given by these points x1, x2, x3, x4, x5. Then the traditional way is we start with the smallest point. Well, we start with the smallest value, and then we order data in the increasing order. So we get the so-called order statistics, and we can rank data according to this order statistics from smallest to largest. However, in the beginning of the 20th century, Harold Hotelling suggested that maybe this is not always the best way to do it. In his paper from 1929 called Stability in Competition, that was related to some questions in economics, he suggested this notion of depth, that maybe we should order the data according to their proximity to zero. So basically, in this case, the way that we can order the data, we can say that this point x1, it is in some sense the central point of the sample. So we'll call it the deepest point, and we'll give it rank 1. Then this point and this point are sort of the next points in closer to x1, and these are the most outer points of the sample. So we'll give them the highest rank. So Hotelling basically explained it as think about the market, and you have maybe this is like the central street of the market, and you want to have your stand closer to most of the customers, right? So what would be the most advantageous place? Well, the most advantageous place would be as close to the central street as possible. And then, so the next best position will be, say, the second street away from the central one, and so on and so forth. So this gives this idea of depth, and we can formally define depth of a point z with respect to any probability measure. So in this case, I just have a counting measure defined by these 5 points, but with respect to any probability measure, I can define depth as the minimum between the depths of two um, uh, uh, essentially of two rays, one half line that is infinite on the left, one is infinite on the right, that are denoted by these orange lines on the plot. And the minimum of the measures will be the depth of my point. Now, what about the case of dimension 2? So what if my problem is two-dimensional? What would be the natural way to, say, order data or assign ranks to data in this case? And it's, of course, a well-known question in statistics. Many viable definitions exist. One of the perhaps more famous one is due to John Tukey, and this one carries the name of half-space depth, Tukey's depth. So here is the famous paper published in the proceedings of the National Congress of Mathematicians, 1970s. And the idea so again, I will explain. Oops, I think my my slides have disconnected momentarily. So what is the idea behind Tukey's depth? So let me assume that I have a sample of 5 points, which are these 5 red squares, and I have the cross in the middle. I want to understand what is the depth of this cross relative to the 5 squares. And the way that I will do it is I will say, so let me choose one direction. So let me choose half space in that goes through my point in this black direction, and then I will project all the red points onto this black line, so we'll get the blue points. So now I have once I have projected my data, I have a one-dimensional problem, and then I can evaluate the univariate depth of my reference point of the cross relative to the projections of the red points. Okay, so in this case, what is the depth going to be? So I have 2 points on the left, I have 3 points on the right. So the minimum is 2, so the depth is going to be 2 over 5, 2/5. Right? And now I will do it for a different direction. Now let me take a different direction, which in this case is green line, with small circles being the projections of the red squares onto this new direction. And what is now the depth of the reference point with respect, again, the univariate depth of this reference point with respect to the little green circles? Well, I have 1 green circle on the left, I have 4 green circles on the right, so the minimum is 1, and therefore the depth along this direction is 1 over 5. Right, so the depth along the first direction was 2 over 5, the depth along the new direction is 1 over 5, and I can do it over all possible directions on the, say, encoded by vectors on the unit circle, and I will take as my depth, I will take the smallest depths among all possible directions. So that was the idea. Okay, I will just keep this picture on for a little longer, and there is an alternative way if you want a different way to think about it. Then again, let's assume I have these 5 points. I have a reference point denoted by the cross, and I will ask the following question: how many points do I have to remove so that this x is not inside the convex hull of the remaining points? So now clearly x is inside the pentagon, which is the convex hull of my 5 circles. If I remove one vertex, then now this cross is outside of the convex hull. And clearly, it is enough to remove just one point, right? It is enough to remove just one point to have this happen. Now, if I put my x kind of almost in the middle of my pentagon, then no matter which point, which one point I remove, it's still going to be inside the convex hull. So in this case, I need to remove 2 points from the original sample so that x is outside of the convex hull of the remaining ones. So this tells me that in the first case, the depth was 1/5. I had to remove 1 point. In the second case, the depth is 2/5. I had to remove 2 points. And so these definitions are equivalent. The first one and the second one are equivalent definitions. And in fact, in this case, I can also compute, I can find all the points of given depth. So if I connect all my points with lines, then this innermost part will be the set of all points of depth 2/5, which is, in this case, the largest I can have. The gray shaded area will be the set of all points with depth 1/5, and everything outside of the convex hull of the original data will have depth 0. Okay? Any questions so far? So hopefully this gives you an idea of depth, what depth is, and it also shows you that so we can ask this question: when do probability measures have points of high depth, right? Or essentially, we will be interested in this talk in the situations when points of high depth exist. So when there are no points of high depth. So if I have, say, if I have d points in general position in d-dimensional space, or d+1 points, if I have d+1 points in general position in d-dimensional space, then the convex hull of this d+1 points is going to be a simplex of some kind. And in this case, the highest so the highest possible depth is going to be of order 1 over the dimension. So somehow I need, if I'm talking about atomic measures, then I need the number of atoms to be larger, significantly larger than the dimension to have points of high depth. Right. So this one of the maybe downsides of depth is that you need more data than the dimension to have to have these points of high depth. And one to also say what Tukey's median is, if the central region is the set of points of highest depth, then Tukey's median is just going to be the barycenter of the set. So this is a traditional definition. Take all the points of highest depth, take its barycenter, call it Tukey's median. So this is the natural measure of centrality, or one of the possible generalizations of the notion of the median to high dimensions. And this is going to be a robust estimator of centrality. Again, if this point of highest depth will actually have a, well, if the depth of this point is actually sufficiently large. Okay. This notion of depth has a very attractive property of being a fine equivariant, which means that these depth contours, they respect the fine transformations, right? Because everything was defined, well, essentially because of the way that everything was defined. If I apply an affine transformation to my data, then the corresponding depth will be preserved. So if I stretch it or compress it or rotate it, then it doesn't change the depth of points. So we'll remember this property. It turns out to be very handy. But on the other hand, this is one of the reasons for the phenomenon that I mentioned before, is that for the depth-based procedures to work, we always want the sample size to be large compared to the dimension. So if I compute the Tukey's median based on a sample of bivariate normal data, then the picture looks something like this. And here you see the different contours. So this convex polygons correspond to the points of different depths. So the most central region is a set of points with highest depths, and the outermost region is a set of points with lowest depths. These are always going to be convex sets. It's one of the properties of half-space depths is that the depth contours are always convex, which is nice. The question that I mentioned in the beginning of the talk is, well, I want to understand how close will this sample median will be to its population counterpart, which for normal distribution is just going to be the mean. So this the point, the most central point is going to coincide with, in this case, with the median as well. So the mean and the median for normal distribution coincide. Another interesting question is, well, if I let my sample size increase, then we see clearly in the picture that, say, for the case of isotropic bivariate normal distribution, these contours become more and more round, so they approach their population counterparts, which are just circles. The question is, how large would, for example, the central set be? So how large is the set of points of largest depths? In the univariate case, we know this by essentially the interquartile intervals. So in the case of dimension one, the set of all medians is just the distance between two consecutive order statistics, and for normal data will be of order 1 over n. But what about higher dimensions? What is going to be the diameter of the set of all medians? And as a corollary of some of the results that I will present later, we actually show that in any dimension d greater than 1, if data come from, say, Gaussian distribution, or more generally, if data come from, say, generalization of Gaussian, the class of elliptically symmetric distributions, then the diameter of the set of all deepest points is small o of n to the power minus 1/2. And in the special case, when d equal to 2, we can say a little bit more. We can say that, in fact, it behaves like n to the power minus 3/4. So the conjecture would be that, at least in the case d equal to 2, this estimate is optimal up to log factors. And more generally, it would be interesting to understand whether there is some possible dimension-dependent delta bigger than 0, so that the diameter of the set of deepest points behaves like n to the power minus 1/2 minus delta. So currently also not known, and then closer to the end of the talk, I will explain some of the underlying problems that one will have to overcome to prove a result like this. Okay. Any questions up to now? Okay, so that I don't go too fast. All right, so let me go back again to the first question that I posed. We have a sample from normal distribution. We have this notion of effective rank. We have a corrupted sample, so the possible epsilon fraction of the data have been corrupted. In this case, it's been known, this paper by Chen, Gao, and Ren from 2015, that Tukey's median actually does satisfy an almost optimal deviation guarantee. The difference being that was this dimension factor present. So somehow it didn't show whether Tukey's median respects this intrinsic geometry of the data. So there's this condition that I also mentioned, that the sample size has to be larger than the dimension. This condition is essentially unavoidable for Tukey's median. But the question was whether for these large samples, whether the distance between the median, between Tukey's median and its population counterpart, is still controlled by the effective rank of the dimension. That's related to this folklore conjecture that I stated before. And Tukey's median was one of the first estimators for which uh, it was probably known that it does have this optimal dependence on the fraction of corrupted data. So as I also said, this epsilon is not multiplied by any dimensional factors, just by this scaling factor. Okay, so can we replace this D by the effective rank that was the starting point for this work? And that what we were able to show is that at least in the contamination-free framework, which is maybe the first step, it was not known even in this case, in the contamination-free framework, it is indeed true that when sample size is sufficiently larger than the dimension, then Tukey's median does satisfy this correct sub-Gaussian deviation guarantees with uh, the effective rank in place of the ambient dimension. And the proof, I will say a few words about it, is quite quite simple, and it just relies. Okay. Apologies about that. My sharing sometimes disconnects. So the proof relies on this property of affine equivariance that I mentioned before. So essentially, what we can do is okay, sorry about that. Okay. So the proof relies on affine equivariance. So one observation that we can make is that, so what does it mean that the estimator is affine equivariant? Essentially means that I can pass any affine transformation kind of inside my estimator. So instead of applying, instead of whitening out my estimator, I can instead first whiten out my data, so kind of decorrelate it, and then compute Tukey's median, right? So due to the fact that it respects all affine transformation, this is indeed an equality. And now we can use the fact that if I decorrelate my data, so if I compute Tukey's median for isotropic Gaussians, essentially, then its projection onto the unit sphere must be uniform, right? So since I started with, if I start with spherically symmetric data, then my estimator is also going to be spherically symmetric, and this fact turns out to be enough to get what we want to do the simple trick. So if I write my estimation error as essentially, okay, this I multiplied by sigma to the power minus 1/2, then I need to multiply it back by sigma to the power 1/2, and then I divide and multiply it by the norm of the decorrelated vector W, then I can write my error as a product. On the first term in this product is the norm of this isotropic vector. So essentially Tukey's median applied to decorrelated data. And the second term is a linear transformation of a vector which is uniform on the unit sphere. Okay, and it turns out that we have good control of both vectors. So the first vector, we can apply the existing result by Chen, Gao, and Ren. Now, since here everything is isotropic, so we can estimate it by the quantity that depends on the dimension. And the second term is, as I said, is just a linear transformation of a uniform distribution on a sphere to which we can apply, say, Levi's inequality, which essentially tells us that this vector has proper sub-Gaussian concentration, and it does have the following error bound. So the point is that this error bound is not controlled by the effective rank. and not the dimension. And when you multiply these two terms throughout, you will see that the dimension here will cancel with the dimension here, and then everything somehow magically works out, and you get exactly what you want. So just uses affine equivariance, nothing more advanced than that. Okay. If the underlying distribution doesn't have this symmetry properties that the normal distribution possesses, then the argument breaks down. Then we don't have this property anymore. So it is crucial that we start with something that has this sufficient rotational symmetry. Now, so what happens if my contamination is non-zero? So for large contamination, if epsilon is bigger than square root of d over n, then of course the question of dimensional dependence, or whether the dimensional effective rank appears in the bound, is not essentially vacuous, because then epsilon dominates this dimensional term. So we don't have to worry about it. So what happens for small values of epsilon? And for small values of epsilon, we were able to prove that, so it's slightly maybe unconventional bound. So what we were able to prove is that the bound for the difference between Tukey's median computed based on the corrupted sample is controlled by this term that we expect for the uncorrupted sample. And then there is somewhat complicated looking quantity, which is essentially this is like a random variable. This is a random variable, and its size is controlled by the amount of corruption, okay, and some term that is smaller than n to the power minus 1/2. Okay, so in particular, what we can say is that if epsilon is sufficiently small, so smaller than n to the power minus 1/2 multiplied by some constant that depends on the dimension, then this term essentially becomes negligible. So for small epsilon, this term becomes negligible, and then we recover the bound that we want. Okay, it is not exactly the bound what we want, so it's because as I said, this is a random variable that appears in the bound, but morally speaking, we do recover the correct behavior of Tukey's median, in the sense that so its behavior is controlled by the effective rank and not by the ambient dimension. So this is, if you want, this is a partial answer to the folklore conjecture, but perhaps the most interesting regime that this bound doesn't cover is what happens when the contamination proportion is exactly of order of this complexity term. When contamination proportion is of order square root of the effective rank over n, when kind of two terms in your bound of the same order of magnitude. The question is, does, in this case, it can happen in principle that now Tukey's median is governed, or the behavior of Tukey's median is governed by the ambient dimension and not the effective rank anymore. So this is currently not known. The second question, well, if we allow the effective rank and the dimension to grow with n, then the argument that we have also doesn't work. And let me try to explain what are the key challenges in the analysis, and what kind of tools we use to try to get this result. So one immediate observation is that to estimate the distance between Tukey's median and its population counterpart, we need to understand the size of the set of deep points, because what can happen? So what can happen if I change epsilon fraction of my data? Well, if I change the epsilon fraction of my data, then the depth of any point can change at most by epsilon. So this is the key fact that makes this whole concept of half-space depth robust, right? Because half-space depth is based on counting. We're just counting fractions of points on the left and on the right, so their magnitudes don't matter, right? The magnitudes of the points don't matter. And if I change epsilon fraction of the data, I can only change the depth by epsilon, and therefore if my point is the deepest point with respect to the corrupted data set, then if I look at the depth of the same point, but with respect to the clean data, the uncorrupted data, then this point must still have very high depth because it could have only changed by epsilon, right? So if I have this Tukey's median computed with respect to the corrupted data, then it must have depth that is greater or equal than the maximal possible depth minus epsilon with respect to the clean sample, uncorrupted sample. So if I manage to understand the diameter of the set of all points with this property with respect to the clean, uncorrupted sample, then I will be able to say how far my Tukey's median is from its population counterpart, right? Because I know the answer for clean data. So the question boils down to understanding the diameter of the set, and so how can we understand this property? Well, now we need to look a little bit deeper into the theory of Tukey's median. So here, let me define this object for you. So let G of E be a Gaussian process. Essentially, it's some random function indexed by the sphere. It doesn't matter exactly what it is. So it is a Brownian bridge, but it doesn't matter what it is for the rest of the exposition. It is some stochastic process. And what is written here, if you look at it closely, then you will understand that this is, in fact, a Legendre-Fenchel transformation from convex analysis. So this is the infimum of a collection of linear functions. And in fact, no matter what I put here, the object of this form always gives me a concave function. So this WG of Z essentially is a random concave function. And it is known, it's a quite classical result, that in fact, the depth process converges weakly to this stochastic process whose trajectories are concave, almost surely. Remember that I said that the depth contours are always convex sets. So you can see some connections here. So essentially what we have is a random concave function that's in one-dimensional case, I can draw it like this. And in fact, it is possible to show that this random function is going to be strictly concave, this probability 1, which means that it is going to have a unique maximum. So this red point here is going to be the unique maximum of this function. And if we think about this function as some limiting, this essentially is the limit for the depth. This is the point of maximal depth. So let me show the picture. So if this is the point of maximal depth, then the set of points whose depth is close to that is just given by this black interval here, right? So this is the level set that corresponds to the points of high depth. And so what we can do with this is we can use a strong approximation result to say that the empirical depth that we're interested in fact can be approximated by its limit, so by this Gaussian process that looks exactly like this, not just in the weak sense, but in the strong sense. So we can construct this object on the same probability space so that the trajectories of the empirical depths and the trajectories of its limiting counterpart are going to be close pointwise. So that's what strong approximation means. And from here we can prove that the level sets. So the level sets that we were interested in. So essentially, this sets on the picture here, that they can be approximated by the level sets of this limiting random concave functions. Yeah, so it's kind of the essence of the argument. And because as I said, this random concave functions have a unique maximum with probability 1, we know that the sets must contract to 0, right? They will all contract to this red point. If we formalize this argument, then we can prove that indeed the diameter of the set of Tukey's medians must be small. So contracts to zero faster than n to the power minus 1/2. And as I said, in the case of dimension 2, there is some additional geometric structure that allows us to get a stronger bound. But unfortunately, the argument does not extend beyond the case of d equal to 2. All right. So one additional implication of this fact is that the picture typically will look like this because the distance between the population median and Tukey's median is of order 1 over square root of n, and the set of deepest points is small o of n to the power minus 1/2, then it also tells us that in fact the population median will, with high probability, be outside of the set of deepest points. So the population median itself is going to be typically far away from the set of points with high empirical depths. So now another open question that I want to add, and this open question is maybe quite surprising to me that it is still open. Namely, can we understand what is actually the depth of empirical Tukey's median? So we know that by definition, Tukey's median is a point of highest empirical depth, but we don't know what this depth is. So it is of order 1/2 minus something divided by square root of n. But what is it? So what is this something, right? So in other words, what is the limit of the depth of the empirical Tukey's median minus 1/2 scaled by square root of n? It's perhaps would be interesting to understand, since we already know so much about this object. But one of the basic facts about it still is unknown. All right. So the last few minutes of the talk I wanted to devote to talking about extensions of Tukey's median, but let me stop here for a second and see if there are any questions.
I have a question that's very vague, but this is the second time in 2 talks that it came up, so I'm going to sort of be tempted to ask this. Right. Being from the outside of this field, a lot of this feels like large deviation theories in the background of this. You give me a Fresnel transform, you have these kind of exponential bounds. I'm just sort of wondering if you could comment, because it doesn't seem like a large deviation problem on the surface of it, but a lot of the tools do look similar.
Right. So if I go to the very beginning, then the question was essentially so the question here is about if you want the non-asymptotic deviation. Mm-hmm. So yeah, think about it the following. So what do you want from your estimator? What kind of properties do you want? So if we think about the classical result in statistics about sample mean of the Gaussian, then we know that we can use sample mean of the Gaussian, the center of the confidence interval. The confidence interval is going to have a pretty small width, right? So you want, if you think about this in terms of confidence intervals or confidence sets, then you want to construct confidence sets that have the diameter that is as small as possible. And the diameter essentially depends on this concentration, right? So the diameter is controlled by how quickly or how tightly the estimator concentrates around the parameter of interest. Right? If you want this probability to be delta, then this is going to be log of 1 over delta. If the concentration is polynomial, then the width of the interval will also be higher. So that's essentially where.
I guess the question I was trying to get, like in the distinction in my world between the large deviation and concentration inequality is the lower bound. Are these imagined to be tight in the other direction? Are you actually getting the right thing from this? Is there like some flexibility in here expectedly or not?
Right. So essentially, in the worst case scenario, if we take this class of all distributions with for which the second moment exists, then we cannot do better than the Gaussian sample mean. Okay. So essentially, this is the best that we can hope for in general. Yes.
Thank you.
May I also ask shortly just one thing? Why is this problem still open that you had at the last slide? What is the reason? It doesn't seem that
Well,
complicated.
okay, so the reason is that essentially, if we want if you want to get a sharp understanding what is happening, as I said, at least in the way that we treat this problem, then this depth is a pretty complicated object. So it's the infimum of some stochastic process over the unit ball. So we essentially here we're dealing, in this case, we're dealing with some random concave function. If we want to understand, what is happening near the point of maxima of these concave functions. So to understand this, we basically want to know what is the slope of these lines around it, right? So what is essentially want to understand, if you want, the geometry of the subdifferential of a random concave function around its maximum, which is a very maybe hard object to put your hand on. So how do you access this, right? It's so far we haven't found a very good technical toolkit to be able to understand this. So somehow we need to connect the geometry of so we want to connect the geometry of this Legendre transform of this process to some geometric properties of the process itself, to say the covariance of the process. And at least as far as I know, the literature on the literature in probability theory have not explored this beyond the case of dimension one. So we know something about the concave majorants of Brownian motion of Brownian bridge in dimension one. But here we deal with a process which is indexed by vectors on the unit sphere. So it's a more complex object. I don't know if my answer is
Thanks. Yes.
shedding
Thank
any
you.
light, but yeah. So there is some underlying problem in probability theory that I would love to see addressed. Essentially, if we have if there is any literature on random concave functions or random convex functions, then I would appreciate any references. So maybe one last slide, I will talk about extensions. So here is also a known fact about Tukey's median. So one of the reasons that this estimator is interesting is it has a pretty interesting limiting distribution. So as I said, the depth itself, so the limiting behavior of depth process is controlled by this random concave functions, which are Legendre transforms of the Brownian bridge. And limiting behavior of the Tukey's median itself in the uncontaminated framework is controlled by essentially convergence distribution to the maximizer of this random concave function. So this red point here, in particular, is limiting distribution is not Gaussian. It is a complicated functional of a Gaussian process, but itself it is not Gaussian. Maybe beyond the univariate case. In the univariate case, Tukey's median coincides with the usual sample median, and if the underlying distribution is Gaussian, we all know that in this case the limit is Gaussian. I see a question.
Yes, please. Thank you for this talk. My question is, how is 2K depth applied in graph theory, for example?
So I can send you a reference if you email me. I can send you the papers that discuss the notion of depth in graph theory, but maybe it will be well, different direction, not something related to what I'm talking about here.
Okay, thank you.
Yeah, but I'll be happy to share references.
Thank you.
So going back to what I was saying is in the univariate case, we know that distribution is normal, and there's also this classical result from the 60s due to Hodges and Lemon said, well, sample median is great. In the univariate case, sample median is great. It has high breakdown point, but it is not very efficient. So they suggested, well, can we increase the efficiency of sample median? They said, let us instead take all pairwise averages of our data. Let's take all pairwise averages, and then let us take the median of these pairwise averages. So what is going to happen in this case, and this is what we know as the classical Hodges-Lehmann estimator, it is known that in the case of, I guess, normal population, its asymptotic variance is of order 3 over pi, so it's very close to, it is almost efficient. It's about 0.995, so significantly higher than so its efficiency is significantly higher than the efficiency of the sample median. And of course, it trades some robustness for efficiency, so it has lower breakdown point. So it was interesting to see what we can do in this multivariate case. Can we define a Hodges-Lehmann version of Tukey's median, and what is going to happen? And I will just give a one-slide overview that we uncovered some pretty maybe interesting unexpected phenomena. So first, how do we construct this Hodges-Lehmann half-space depth? So basically, what we want to do is we want to take here not the average of 2 points, but we want to take averages of a larger number of points and see what happens. So effectively, the easiest way to think about it is to think about a new sample. We create a new sample by taking averages of all possible subsets of m points. So I start with a sample of size n. Let me take all subsets that consist of m points, and let me take averages of all such subsets. I call this new sample z, and let me compute now Tukey's median with respect to this new sample z. So okay, technically, if I write the formal definition, it's quite technical, but basically it's just the usual Tukey's median computed for this new sample. Now, of course, the complication is that this is not an IID sample anymore, right? The sample averages are dependent because I introduced dependencies by somehow mixing my data. So the object that we get here, the definition of the depth with respect to this new sample is an example of what we call a U process. So it's an extension of this notion of U statistics. And again, the main difference between it is different from say the usual empirical processes, because when we talk about empirical processes, we deal with independent data. When we work with U processes, then we essentially deal with some notion of dependency. And what we were able to show is that if we now compute this Hodges-Lehmann version of Tukey's median, and if we let the order of this median, so the number of points that I average, go to infinity, then surprisingly, the limiting distribution of such a median is again normal. And effectively, what it means is that such an object is asymptotically equivalent to the sample mean. So as I increase the order of my median, then I converge to the sample mean. So not only it becomes asymptotically efficient in a way that the limiting covariance is just the covariance of my original data, but also the distribution itself is not a complex functional of a Gaussian process anymore, but it is just multivariate normal. And moreover, we can show that this estimator also satisfies a version of a non-asymptotic efficiency in a way that it satisfies this deviation guarantee that is not just similar to the deviation guarantees for the Gaussian sample mean in form, but it is also almost optimal up to numerical constants. So we have to pay this additional factor of 2, but otherwise it is almost exactly like a deviation inequality for the sample mean of the Gaussians. And we conjecture that this 2 can be in fact replaced by 1, that it also satisfies this very strong non-asymptotic form of efficiency, right? That's the constants in the deviation bounds are essentially optimal. And the key technical innovation that I'm not going to mention in this talk, I'll just say that to get this type of results, one has to obtain a sharp deviation inequality for U processes, which essentially generalizes, if you want, generalizes Lagrange inequality for empirical processes. we have to extend it to this case of dependent data. Okay, so I will stop here. Thank you for your attention, and if you have any additional questions, happy to answer.
Thank you so much. If anyone has a question, please unmute yourself and feel free to ask.
Thank you very much for the great talk. I have some questions. Your proof introduced this Brownian bridge concave limit. And do you think this method could be extended for other notions of depth, like projection depth?
Sure, I believe it's one could do it. I think our method, let's say, this method is it was largely motivated by the necessity, because it is difficult to, since the definition of Tukey's median is in a way implicit, so it is defined as a solution to some optimization problem, right? So we have to find some workarounds. We had to find some workarounds to deal with it, and because we had to use this strong approximation results, then it necessarily results in maybe loss of some maybe loss of precision in the bounds. So I guess not all notions of depth are created equal. So maybe for some notions of depth, maybe you do not need to do it. But in principle, if you wanted to develop the proof that parallels this proof step by step, you could do it. So you could divide it into some building blocks, and if you manage to show that the other notion of depth has also some concavity properties, like we have here, then the argument would work. So here it just happens to be that this limiting process has this nice property that it almost surely has unique maximizers. It is not in general guaranteed to extend to other situations.
Thank you. And also in dimension 2, the diameter rate, it was something like n to the minus 3/4,
Right.
and there was a log factor. And this log factor, like this is the sharp of this log factor is intrinsic, or it comes from the proof?
The log factor, I don't know whether it's sharp or not. It comes from, essentially, it comes from this strong approximations. Or there are several terms. So there are several terms in the bounds. One in dimension d equal to 2, essentially everything is governed by the strong approximation terms. It is it turns out to be n to the power minus 3/4.
Thank you very much.
Essentially, what we can show in dimension 2, the picture looks exactly like this. So in dimension 2, we can show that around the point of maxima of this random function, the decay is linear. So the function decays linearly around it. In dimension 3 and higher, we can only show that the maximum is unique, but we cannot really get a better control on the rate of decay. So that's why in dimension 2 we have a sharper. That's why we have a sharper bound.
I see. Thank you.
May I also ask just an additional one question? Thank you. Thanks. It was very interesting, both presentations. Again, similar like for the first one, depth concept is known from some area of statistics, naturally, functional data, non-parametrics. But how does this behave if the underlying stochastic process and say space is very so singular, very different. Does this always exist, or does it pose any problems in more complex processes, perhaps even for non-real data, complex data or something? Thanks.
So I'm only aware of so I'm only aware of the notion of depths applied in say standard Euclidean spaces, dimensional Euclidean spaces. So I guess because it comes from this very practical considerations, John Tukey was very practically focused. So I don't know much about extensions to other spaces. Maybe geometry literature will have more. So I would look at works of Stanislav who describes a lot of interesting connections to the notions of floating bodies in geometry and other things that maybe you'll be able to find some interesting directions in there, but I don't have a good answer right now.
Right. Thank you. Thanks.
Okay, if there are no further questions, let's thank both the speakers for the great talks. Everyone clap, everyone do their thing. And we will end this session for today, and we will meet everybody back here in 2 weeks for the next One World Probability Seminar. Thanks everyone for coming.
Thank you very much. Thank you. Thank you.
Fine.
Bye.